Hi there, welcome to Telefunken. Today, we're taking a bit of a departure from our regular fare. Those of you who are new to the channel might not realize that we normally feature vintage electronic musical instruments. But today, we're going to feature the repair of a vintage stereo receiver, the Technics SA-202. The truth of the matter is, I was asked to undertake this repair on behalf of a good friend of mine, so I'm doing so and documenting it in the process. Some of the techniques that we'll be sharing in this video might be useful to those of you who are interested in other receivers of similar vintage. The Technics SA-202 was made by Technics in Japan in the years 1980 to 1981. Nominally, it had a power output of about 30 watts per channel into 8 ohms and a frequency response range of 7 Hz to 45 kilohertz. It claims to be able to make full power with only 0.04% total harmonic distortion, and it has two curious tone controls, that is both bass and treble, of course, but the frequencies that are specified in the service manual are 50 Hz and 20 kilohertz for each. Thankfully, the service manual for the 202 contains a pretty detailed PCB layout and labeling and identification of specialty components such as the various ICs that are scattered throughout the circuit board. It also contains a number of helpful reference points where voltages can be measured on a functioning unit, and this helps in the diagnosis of any faults that we may find. So we have here on the bench a Technics SA-202 stereo amplifier circa 1980 or so, and it's been brought to me with a number of complaints, just not performing properly. And after hooking it up, I can see indeed that is the case. I've got my iPhone playing into the auxiliary input here, and I'm getting no sound at all out of the right-hand side. And this sound that I'm getting out of the left-hand side is quite distorted. Other than that, the bass, treble seems to be working, the loudness seems to be working. I am getting an FM signal if I try to tune it without an antenna, etc. So various other things seem to be operating properly, but there's something wrong with the amplifier section of the instrument. And as just a little hint, I plug in my headphones and I don't get any sound out of the headphones on the right-hand side either. And that may be something that helps us narrow down the problems once we open up the amplifier. So I will indeed open up the amplifier and see what we can see on the inside. You'll notice as well there are other issues such as the light in the and the tuning indicator isn't working properly, and it doesn't really matter what setting we have it on. That light is not lighting up the dial. So we'll see if we can bring this thing back to life. I'll open it up and be right back. This is the inside of the Technics SA-202, and it's filthy, and I haven't done anything to clean it out. I'll blow it out with some compressed air. But what I wanted to do was have a look at it before I remove all of the dust. And what that might do is make it easier for me to see if there's any components that, for example, have exploded. If we have an exploded transistor or capacitor or something like that, it'd be more obvious. It'd be more obvious now than later. I don't see anything terribly obvious. I just see a whole heck of a lot of dust. I do see a lot of old capacitors, including some of these old lilac capacitors, which are famous for shorting, and we can check some of these out. But another thing that is obvious here is that we have a lot of integrated circuits, and I know this about this amplifier, that a lot of the amplification takes place within these integrated circuits. And so one or more of those may be faulty, and although that might be difficult to diagnose, I believe that all of the integrated circuits are still available. And so if we have an issue with that, hopefully we can get the part and fix this. Other than that, all the other parts are fairly standard, you know, these capacitors and so on and so forth. They deserve to be replaced, the amplifier being now 40 years old. So it really would benefit from a recapping, which wouldn't be a too terribly difficult job. But in the meantime, first things first, let's see what is wrong with the amplifier and see if we can fix it. Rather than relying on discrete circuitry, the 202 offloads various functions to integrated circuits, including the AN7001ST, which is an AM/FM stereo receiver and demux chip, which is no longer obtainable, nor are a number of amplifier chips such as the AN7060 or the AN6876. But really, the heart of the 202 is the STK-0029N. These are amplifier modules which were built by Sanyo and are now essentially unobtainable through regular vendors and have to be sourced online through a variety of suppliers who sell these chips on eBay. The STKs are power amplifier chips, and there's one for each side of the receiver, and they mount here in the middle of the circuit board in the areas delineated by the red rectangles. They're connected to the heatsink, which is also cooling a power transistor, which is also connected. A full schematic for the 202 is also available in the service manual, and other copies are available online. As the one in the service manual is of dubious quality, the schematic can be broken down into a number of component areas. On the upper left-hand side, we see the section which is responsible for the FM and AM reception. There's a phono preamplifier containing a couple of other integrated circuits. The power supply section is located on the bottom right, and that feeds, of course, the entire receiver, but we're most interested, as you'll see in a moment, in the preamp and tone control sections, as well as the section immediately prior to the speaker outputs. That is the power amplifier section of the receiver. Here you can see I've zoomed in on the preamp and the power amp sections of the receiver, and I've colored in some of the elements of the circuit to help with my diagnosis and repair. You can see, for example, the ground, which is colored in green, is attached to both negative terminals on each set of two speaker outputs. The receiver has a main speaker output, left and right channel, and a remote speaker output, left and right channel. You can see these on the extreme right-hand side of the schematic. The headphones are powered by the power amplifier outputs and impedance matched by virtue of a couple of resistors that are on a subboard where you plug in the headphone into the headphone jack. The STK chips are represented by IC 603 and IC 604, which are in the middle of the diagram, and then the preamplifier section is to the left, and we see that that is containing two AN7060 differential amplifier chips. You can see that I have drawn in the positive and negative voltage supply rails in red and yellow respectively, and that they connect directly to the STK chips. Here you can see the right-hand side STK circled in red, and if we zoom in a little bit, you'll see that the various voltages that should be present on the chip are indicated on the schematic. They're also indicated on the PCB layout diagram. We should be able to check the chip in circuit and find that these voltages are present on the chip. And actually, with the chip out of the circuit, these voltages should be very similar to what's shown here. And I'll describe how we check for this a little later in the video. Of course, one of the best places to start when assessing the health of any electronic equipment is to look at the power supply. And we know that the power supply is producing some power because we can turn on the amplifier and we do hear sound coming out of one of the speakers. However, it's always a good idea to check the integrity of the power supply and make sure that it's producing voltage on each rail. In this case, we have a bipolar power supply, which takes the AC 120 volts in and converts that to 26.8 volts per side in a center tapped transformer. And upon bridge rectification, that should correspond to roughly 37.2 volts DC. According to the service manual, the power supply should be providing 35.5 volts DC on each of the positive and negative supply rails, and these should be present on the STK power amplification chips. One of the things that I discovered quite early on when looking at the amplifier is that although the power supply filtering caps or reservoir caps are indicated here as being 45 volts, 6800 microfarads each, the capacitors that were installed in this location were actually 35 volts, which is terribly close to that 35.5 volts that they're experiencing all the time that the amplifier is turned on. So after confirming that the power supply was indeed functioning and providing both a negative and a positive supply rail, I turned my attention to the STK amplifier chips, and as you may be able to make out on this diagram, the negative and positive supply should be provided at pins 2 and 9 respectively on each chip. And when I went to measure these voltages, I found that the voltages were very different from what should have been supplied at the chip. The other voltages present on the chip, for example on pins 1 and 3 and 8 and 0, are actually the input and output of the amplifier chips, and these should be quite low voltages. However, when I measured them, they were all out of whack. So I pulled the chips to take a look at them out of circuit and began to try to diagnose what was going on. Well, this is the SA-202 after I've had an opportunity to examine it and determine what was and was not working. And as you can see, you should be able to see, I've removed quite a few parts from the amplifier or the receiver. Although most of the faulty parts were actually in the amplifier section of the receiver. But you'll see, for example, that I've removed the 2 amplifier modules, which were located here. I've removed, of course, the heatsink, which was mounted from here to here for these modules. I've removed all of the electrolytic capacitors from the power supply section, which is over here, the amplifier section, which is here and here, the preamplifier section, the phono amp, and the AM/FM receiver section, which is this section here delineated by this dotted line. And so we are missing quite a few parts now, and this is a result of many of them being out of commission, and I'll show specifically what I mean after I film a flyby with my newly acquired macro lens. So hopefully this works out well for you and you can see, get a little bit closer here to the receiver and see all the locations where electrolytic capacitors should be located. And that includes capacitors that are used in filtering the power supply, such as this section here, C701, 702, all the other smaller capacitors as well. You can see where the amplifier modules go. These are located in these areas delineated by the rectangular box with a space for 10 pins. These are where our Darlington amplifier modules go. And then a whole array of other capacitors which are located underneath this little shelf here, which is part of the tuning mechanism. But again, there's a whole range of electrolytic caps that go under there, and they've been removed, as has the dial light indicator section of the instrument. This dial light assembly has 10 incandescent bulbs which provide the soft lighting to the front of the receiver. Every single one of these little incandescent bulbs is burnt out, and so I'm in the process of designing a LED replacement configuration that will work in place. These bulbs are powered by 8 volts AC, and of course LEDs require DC supply, and so I'll be figuring out a way to power 10 LEDs in place of these bulbs. The bulbs were 8 volts, 80 milliamps each, and as such were drawing almost an amp of power themselves just to light up the front of the dial of the receiver, which seems a bit silly. So in terms of the actual parts themselves, these are the dead men. And what I've done is I've examined these both in circuit and out of circuit. And what I can tell you is that when one looks at the schematic for this receiver in the service manual, you can see various voltages that should be present on the amplifier modules. And so that was a good place to start in my diagnosis. These amplifier modules go right here in terms of the PCB. And one of these amplifier modules, this one, has a short across the input and the positive power supply. So of course that's not going to function properly. And the other one is not providing the appropriate voltages when in the receiver, and so I believe that's not working properly. These large filter caps did test okay, but I removed them regardless because they're now getting on 40 years old and might be slightly underrated for their actual application. These are rated at 35 volts and they're seeing 35 to 40 volts actually on the power supply. So even though they tested okay, we'll be replacing those. Many of these capacitors did not test okay. And this is an example where we have a 220 microfarad capacitor, and we can see a number of things that suggest that this is highly stressed. So first thing we can see is that it's burnt. It's black on the outside. We can also see that the plastic coating on the outside of the capacitor has retreated back after the capacitor has swollen. So this is another capacitor of the same value. So these should look identical to one another, but they don't. You can see that the capacitor on the left-hand side, the plastic sheathing has peeled back relative to the one on the right-hand side. And at the same time, the one on the right-hand side, the bottom is bulged a little bit. So both of these actually test poorly and need to be replaced. There are many other capacitors. This is another example where a capacitor is swelling and the plastic sheathing is peeling back. And we can compare it to this one, which is actually reasonably healthy. This one with the little orange dot on it is testing better than its partner. And there are many other examples where we can see issues. And I'll try to show you some examples of smaller capacitors where we see corrosion on the legs of the capacitor. And I don't have my glasses on, so this is a little difficult for me. But this one, for example, if we look at its legs, you'll see some green copperish colored discoloration, corrosion, and this is actually a result of the potassium hydroxide, which is the electrolytic inside the capacitor leaking out and corroding the legs. And so we have lots of capacitors which have started leaking, and this is leaking physically, meaning that the potassium hydroxide is actually coming out of the bottom of the capacitor and starting to destroy. Here's, I think, a good one where you can see this. It's starting to destroy the lead on the capacitor, and it'll actually destroy the trace on the printed circuit board. And as a result of this electrolyte leaking out of the capacitor is not going to perform electrically and will begin to leak electrically, which is to be distinguished from physical leakage of the electrolyte. It means that they'll begin to conduct DC voltages and begin to act more like a resistor than a capacitor, and we don't want that, obviously. So all of the capacitors with these red dots have been tested for their capacitance and their equivalent series resistance and have failed. And so even though there are some that appear to be functioning properly, like this one, they've all been pulled out and will all be replaced. So what does something like this cost? Well, the capacitors themselves, these two are kind of expensive. They're maybe $4 or $5 each. These range from, say, 20 cents to 70 cents each, depending on the size. So maybe there's 20 something odd dollars worth of parts here, but really what it's coming down to is the time that it takes to do this sort of thing. So is this receiver worth it? Well, it depends. It's not worth the money to fix it, but in the end, when it is fixed, it should be a very nicely performing, nicely functioning receiver. And so I hope that the owner appreciates all of this effort. This is being done on behalf of a good friend of mine who has asked me to fix this on behalf of a friend of his. So I haven't even met the owner of this receiver, but I'm going to do the best job that I can to get it right back into the condition it was in when it left the factory. And hopefully that is appreciated by everyone concerned. These are the power amplifier modules, and they are no longer obtainable through regular channels. So I've ordered 2 of these from eBay, and I've ordered them from a supplier in Canada that supplies these types of modules for amplifiers. And hopefully I'm not procuring counterfeit versions, because the internet is rife with counterfeit versions of these types of chips, these integrated circuits with specialty function that have relatively high value. So these are about $10 each from the vendor that I procured them from. And I paid a little bit more than I had to, because I didn't want to get them from China, where it is known, unfortunately, that there are a number of vendors that are specializing in counterfeit parts. So that's a quick update. I'm going to repopulate the receiver with brand new capacitors. I'm waiting for the arrival of these, and I'm designing the circuit for the illumination of the front panel of the receiver. But I thought I'd provide this brief update, and when I've finished with the repopulation, prior to the insertion of new amplifier chips, I'll be testing some voltages and probably share some of my findings in that regard with you. I've made some progress on the 202. It's now been recapped and cleaned up a little bit, and I've still got the modules, the amplifier modules, out of the receiver. These are the TK STK-0029s, and I have a couple of these on order. But in advance of receiving these and installing them, it's possible to check some of the circuitry and determine whether or not it's functioning properly, because what we don't want to do is put in new modules and then simply blow them because the circuitry feeding the amps is faulty. And so in order to test the circuitry around the amplifiers, what I've done is I've soldered in resistors across pins 1 and 3 and pins 8 and 0. These are 1 kilo ohm resistors soldered in, bridging these pins. And this allows us to power up the amplifier and measure some of the voltages at the pins on the this module, and also on the differential amplifiers that precede them in the schematic. And what I found in the course of doing this is that there's a couple things going on, in particular with the right channel, which is the one that was most seriously blown. And one of the things that's going on is that we have a blown transistor, Q602, which bridges the differential amplifier and the TK-0029, the STK-0029 amplifier modules. And I've pulled that out and analyzed it. We'll look at that in just a moment. The blown transistor is a pre-drive transistor that sits between the AN7060 differential amplifier and the preamp and the IC604, the STK chip, which is the power amplifier. So here we have Q602, which is a 2SN, I believe it's a 2SN 1123. 2SA 1123. It's a 2SA 1123. And so let's stick this in our little component tester. We see that it tests as 2 diodes rather than an actual transistor. Now, of course, transistors are analogous to back-to-back diodes, but they are not actually 2 diodes. And so this transistor is faulty. I'll just test it again, move its legs in the tester, and confirm that it is not testing as a functioning transistor. And there we go. Again, we've got 2 diodes coming up. And this is something that is a little difficult to test in circuit. It did not show up as a short, for example. And if you're testing with a simple multimeter, you might expect your transistor to show up as a diode when you're testing each section in isolation when it's in circuit. And so it's a little bit difficult to find this kind of failure. But nonetheless, we found it, we pulled it out, and I've got a couple of replacement transistors here. Another thing that I have done is I have put in some lighting on the front panel, and the front panel had incandescent bulbs, and I've installed LED lights, and you can see that's the character of the LED light that's produced from 10 warm white LEDs mounted in the circuit board that previously housed the incandescent lights. And I've put in actually a bridge rectifier board and a trimmer potentiometer to adjust the brightness. And so that should work for many years. So what's next? After pulling this transistor, I find that we still have faults in the right-hand side section of this amplifier. And in particular, we've got a very high negative voltage coming in this pin here, pin 1 of the STK, and it should be a very modest negative 1.2 volts, and it's about minus 29. And so I need to track this down and figure out what component may have failed and is contributing to this, and replace these transistors. I've also pulled the differential amplifier and I'm testing that. And it is not the easiest thing to find, a replacement differential amplifier, an AN7060. They don't make them anymore. Got a couple of those on order from Spain, of all places, in case this guy tests poorly. Another issue with this is that many of the chips that are branded as AN7060s and available online on eBay and the like are counterfeit, analogous to the situation with the STK 0029s. And so again, I'm hoping I haven't just bought a couple counterfeits. So that's the update on the progress thus far, and I'll be back with another one once I've replaced these transistors. In an effort to determine what was causing the aberrant voltages around the STK chips, I turned my attention to the various other discrete components in the preamplifier and power amplifier section of the receiver. I verified the value of every single resistor in these sections. I made sure that each capacitor was not shorted, nor were they open, but they were actually still intact and functioning as capacitors. And once I had confirmed that all of the discrete components were in good shape, I turned my attention to the printed circuit board itself, and I examined the PCB for eroded or corroded traces, and I observed something that I thought was a little strange, and that was that in a number of places where jumpers had been soldered onto the PCB, these jumpers had been cut such that the ends were really quite long, and that necessitated folding them down onto the board. And in many cases, the jumper leads were actually contacting adjacent traces, potentially leading to short circuits. And so where I found those types of situations, I trimmed the leads, pulled them a little bit off the board after doing some desoldering, and made sure that there were no shorts between traces where there shouldn't have been any. After undertaking this and a general reflow of this section of the receiver, which would address any aberrant connections that might have resulted from physical stress or corrosion potentiated by the potassium hydroxide leaking from the capacitors, I found that the voltages magically restored themselves to the values that they were supposed to be, consistent with my expectations, given that I had soldered these 1K resistors across the relevant pins on the sockets for the STKs. So with that resolved, I was at a stage where I was ready to put in the new chips once they arrived. So I've received the replacement chips, the STK 0029 chips. These are Sanyo power amplification chips, or Darlington power packs, as they're sometimes referred to as. And these ones here on the left-hand side are the ones that came out of the amplifier. And this one here is the right-hand side chip, which, as you'll see, has a short in between pin 9 and pin 0. And so this one is obviously no good. And so this is the one that was functioning. And then these are our two replacements. But you'll note that the two replacements come from different lots, presumably, as indicated by these codes here, which are usually manufacturing codes, which will denote the year and the date of manufacture. So for example, this is probably 2015, this is 2014, and so on. Some combination thereof. Not really necessarily concerned with exactly when they were manufactured. They were both obtained from the same vendor, although one of these was shipped at a different time. I ordered two, they shipped one, I had to wait. So all in all, it took me about 6 weeks actually to get these darn things. And that was even from a vendor here in Canada. So let's compare these two new chips to the old chip, the original chip. And we're just going to look at the resistances across some of the relevant pins. So for example, we have on this pin, and this is an operating chip. If we go from pin 1 to pin 2, with that polarity, we have an overload. We can't measure a resistance. And similarly, we seem to have an open here if we go between pin 1 and pin 2. However, if we're over here, we can measure about 28 megs and an overload if we go on this polarity. So let's compare. With this chip, we have about 33 megs. With this chip, we have about 35 megs. And if we reverse the polarity, we have an overload and we have an overload. So that's very encouraging. I would say that's encouraging. What about between pins 8 and 9? Well, we have an overload with this polarity. If we change it, we still have an overload between pins 8 and 9 on this chip. Well, we have about 13 meg here. And curiously, we have about 180 meg here, an overload. Well, that's odd. 14 meg. And an overload. We reverse the polarity. We've got about 7 meg. Here we reverse the polarity. We've got about 0.4 meg. So these are obviously not the same. So whether or not they perform in circuit or not remains to be seen. We'll pop them into circuit and see what happens. But I'm not holding my breath. So we'll mount these guys on the heatsink and go from there. So this is our heatsink, and it is to be used to secure the these STKs, and they are mounted in this orientation, clamped onto the heatsink, directly onto the heatsink with no pads or anything insulating them, no insulation pads, and then this heatsink clamps onto the PCB. So I'm going to mount these first. There's also a mica pad that goes here for one of the power transistors in the system. This is, I believe it's this guy over here. This power transistor, yep, Q701. And so it has a large heatsink right here, or rather is mounted onto the heatsink. And so we will be installing the mica pad there and making sure that we've got good thermal transfer. In the meantime though, I'm going to start by putting heatsink compound where these mount. And again, it needs to be in a rectangular shape to give good heat transfer between this metal surface and the heatsink. And there's no point in putting compound all over the place anywhere beyond this little rectangular area that I've indicated. I'm not sure if you can see that. I've drawn it in a red felt pen just to give me a little bit of a guide. So the way that I prefer to do this is take a cotton swab and get it coated with the heatsink compound, and then use it to apply the compound onto the actual heatsink itself. And what you want to do is paint on a relatively thin layer. The reason why it's white is so you can see where you've gone and you know that you've applied a layer of heatsink compound. But for better or worse, that means that if you apply too much and you end up spreading it around your board or whatnot, you're going to see it everywhere, and you get it on your hands, your clothes, etc., etc. So just try not to, just be careful. Try not to use too terribly much of this stuff. Because it can make quite a mess. So relatively smooth layer there. You want to get a fairly uniform layer if at all possible, without any bald spots, so to speak. Okay, so we have this guy here, and we'll place it right here. And lock it in with the screws. Wiggle it around just a little bit to smooth out that heatsink compound. Give it a light touch on the screwdriver. Wait till the other one is in, until we tighten these up. So I find this approach tends to spread stuff around a little less than if you try and put the compound right on the device. In some cases, you have to take it on a case-by-case basis. With the power transistor, we're actually going to have to put the pads on the heatsink, then install the heatsink, and then clip the transistor onto the pads. So there we go. We see a thin layer of heatsink compound which has been pressed to the edges of the device, and that's adequate to facilitate transfer. We certainly don't want any more than we have on this device here, and I'm sure that this is adequate, given that although we don't see any coming out beyond here, the corner of the heat transfer section of the device is about right here. So we've got, again, plenty of compound on both devices, even though we have a little bit more on this one over here. So that's fine. Now, with respect to the mica pads, I knew they were here somewhere. This mica pad is slightly delaminated. Not a huge problem. We won't use the thin section that came off. And again, we use essentially the same technique, which is that we apply the compound quite liberally in the area where we know the pad will sit. In this case, however, we apply the pad then we apply more compound on top of that pad, and this compound is what will be up against our transistor. Actually, maybe I'll just put it on the transistor. Change my mind there. I'll move the amp into position, and then we'll install the heatsink. So we have the heatsink with the power packs mounted on them and the mica pad for the power transistor, which is located right here. And now the trick is to get the heatsink into the chassis and in the correct position so that we can secure it while getting these pins in the right location. They've been cleared of solder. They're obviously right here. That's the location where the power packs mount. And ideally as well, making sure that we don't cause any damage to the power transistor or any of the other components. I'm going to put some compound on the back of the power transistor and hopefully not get too terribly much of it scattered around the board. And apply some to the actual mica pad as well. And move these wires out of the way. And there we go. All the pins are through the board. There's no strain on any components. The mica pad is fully insulating the power transistor. And we have a minimal amount of heatsink compound distributed where it's not supposed to be. So the power transistor is secured by a metal clip that clamps over the heatsink and then screws onto the heatsink and presses the transistor against the board. Now it's only allowed to come into contact with the plastic enclosure of the transistor and should not be touching the metal portion of the transistor at all. Otherwise it would result in a short to ground. So that's installed and it's pressing the body of the transistor against that mica pad and the heatsink. So the heatsink is bolted down, the clamp on the power transistor is clamped, and now we can turn the board or the receiver upside down and look at the other aspects of mounting the heatsink and then actually soldering on the power packs. So we've flipped the SA-202 on its back and can now solder these in. In the meantime though, I've also attached this bracket which fixes to the bottom of the PCB, and it is used to provide a surface that we can use to screw the bottom of the actual receiver onto, which is here. And so when the time comes, we'll be mounting to this and this. So in the meantime, I will solder in our new power chips. And I'm going to be alternating from one to the other so as to not overheat anything. Warming first the pad, using the pad to melt the solder. Keep in mind these are integrated circuits, so we want to be sort of gentle. and we'll clean up some of this flux. So we'll plug it in and do a smoke test. Hopefully we're not going to let any of the magic smoke out, especially out of our new components. We have had it on previously, measuring the voltages that the STK, the new STKs will be subject to. So there shouldn't be anything present that the amplifiers or the amplifier chips can't handle. And so I have the amplifier plugged into a variac and an electronic circuit breaker and an isolation transformer. And I've set the electronic circuit breaker at 1 amp, and that 1 amp should be more than adequate to power on the amplifier. And we'll power it on and see what happens. So we have power, no magic smoke so far, and time to test the amplifier and see what it'll do. So we have the 202 turned on and the volume is all the way down, and I connected a function generator through, well, it's really an app running on my iPad, which is good enough for our purposes for the time being. And I will turn this up to about minus 3 dB according to the way that this is calibrated. And it's at 500 Hertz. And so we should be able to hear that. I have the 202 connected to my dummy load and digital oscilloscope, the analog discovery, mounted in this chassis. And we're currently set up so that we can use the internal speakers that are built into the dummy load to confirm that we actually have a signal that we can hear. And we do. You'll hear that. And if I adjust the balance, turning it all the way to the left, we hear it. All the way to the right, we hear it. This one of the speakers is on the other side of the chassis. But there we go. We appear to have signal coming out of both channels. If I adjust the treble, we're not going to hear much difference. Very little difference if I adjust the bass. But again, that's because we're listening to just a pure 500 Hertz tone. I'll turn down the volume a little bit and send through a noise signal. We'll send through white noise. And so the treble is working and the bass is working. So treble on the right channel and bass on the right channel. On the left and on the right. I can hear the difference. You may not be able to hear the difference. But again, that suggests that they're both working. Loudness profile is making a change as well. So we'll turn that off, and we will turn off the speakers so that we can begin to see what kind of power this amplifier is going to make. So we're sending a 1 kilohertz tone into the amplifier, which is turned on and connected to a dummy load, an 8 ohm dummy load, which is in turn connected to the analog discovery digital oscilloscope. And we're recording the signal as measured by the oscilloscope. So if I turn it up, we see 2 sine waves, and they track with one another. They're offset slightly so that we can see them both. And then as I keep turning it up, I get to about 16, maybe 15.89, 15.8 volts RMS. And so that is the peak output power I have this amplifier at 1 kilohertz, and in order to find out what that corresponds to in terms of watts, take 15.8 times 15.8 divided by 8 ohms, and that equals 31.2 watts. And the amplifier is rated at 32 watts into 8 ohms continuous power, both channels driven. So that's pretty darn close, although we're getting slightly less, 0.8 watts less than what it's rated at. And that could be for a number of different reasons. So we've had some success. We've repaired the SA-202 and it's working as it should. So what can we say about this receiver? Well, its good points are, in my mind, that it looks great. It's got that classic silver face look from the 70s. And it wasn't really too long after this that Technics and various other manufacturers moved towards black-faced equipment. And that's what you'll see all the way through the 80s. And personally, I think that stuff looks terrible. In fact, there is a black-faced version of this receiver. So this is really on the cusp of that turning point, moving away from that silver-faced design to the black-faced equipment. The printed circuit board in this receiver is pretty high quality. None of the traces appeared to be about to come off the PCB, so it was well manufactured. And this is in contrast to various other PCBs that I've looked at from other equipment manufacturers around the same era. In particular, I've had a terrible time with Sony PCBs where the traces seem to want to fall off PCBs of a similar vintage. So I'd say that's a good plus. In addition, because Technics is really Panasonic, they're utilizing really high quality Panasonic caps throughout the design. And in spite of the fact that we had overheating and a lot of blown caps, some of the caps really were very good upon manufacture, and some of them survived to this day, 40 years after manufacture, in spite of the abuse that the receiver was put through. Another plus could be the Sanyo STK 0029 chips. Now, in spite of the fact that these are no longer available, at the time they were released, they were reasonably highly regarded. They have good performance specifications, and as long as you treat your receiver properly, they can last for quite a long time. Now, they're not indestructible, and once they're gone, they're gone. As I said, they're not making these anymore, although there are a number of knockoffs that are available. They're of variable quality, and it's not known if some of them are actually integrated circuits or simply Darlington transistors, which have been inserted into chips which resemble this integrated circuit package. Another plus could be the no-frills design. There's not a lot of extra bells and whistles on this receiver. It was one of the receivers at the bottom of the range at the time, but its simplicity is, in my mind, a bit of a positive. So what are the negatives with respect to this receiver? Well, I did find it curious that the EQ set points were at frequencies that I believe have relatively little utility in the real world. So for example, the 20 kilohertz set point is above the limit of normal human hearing. And if that's really the cutoff for a shelving filter, or even the midpoint for a parametric filter, that's not appropriate. So either that specification is incorrect, or they just chose a very strange filter set point. The 50 hertz on the bottom end, again, I'm not sure that that's the best frequency to select for a bass control. I personally would have set it maybe at around 120 hertz or maybe 80 hertz, but 50 hertz is a little too low. All you're really affecting there are the sub-frequencies, and many speakers are not going to go below 40 hertz unless you have really gigantic speakers with 12-inch woofers and the like, which were popular around this. In order to illustrate this point, I'm going to play two test tones. The first will be a 50 hertz test tone, which is ostensibly the frequency set point for the bass control on this receiver. That 50 hertz tone will start now. The second tone will be a 20 kilohertz tone, and this tone is the set point for the treble control on the receiver. This 20 kilohertz tone will start now. So if you could hear that, you've got much better hearing than I do. In fact, you really shouldn't have heard that at all, because 20 kilohertz is at the upper range of human hearing. Your dog might have heard it, perhaps your cat's left the room, but it's not a particularly musical frequency, and accordingly, not a great set point for treble control, at least in my opinion. Another downside to this receiver is its relatively inefficient cooling. The heatsink, in my mind, is a little underwhelming, given that the power packs are capable of 30 watts a side. That's 60 watts, and it would have been nice to see a slightly beefier heatsink. One of the major curious points, though, is that the receiver wasn't really built to its design specifications. So some of the capacitors in the receiver are under-spec'd, 35-volt rated capacitors in a receiver that's seeing greater than that on the power rails. And these are the main power filtering capacitors. To me, that's under-rating. There's maybe an over-reliance on integrated circuits, and the use of the non-metallic particle board chassis is, in my mind, a bit of a downside. Another downside would be what I would consider dodgy assembly of the printed circuit board. The printed circuit board itself is great. However, various parts, well, most predominantly the jumper leads, were trimmed such that in many cases they're bent over and actually touching opposing traces. The only thing that is preventing them from shorting out on these traces is a solder mask and the conformal coating that covers these traces. So this is an example, I think, of assembly in a factory where the people who are actually doing some of this assembly are sitting on an assembly line and don't really know a tremendous amount about electronics. So we come back to the question, what the were they thinking? Did Technics not know how to build amplifiers? Do they not have the talent? I don't believe that for a nanosecond. The folks who designed this amplifier knew exactly what they were doing, and they make fantastic parts. They did at the time, and they still do today. They used some of the best parts that they had available to them at the time, but at that time, Japan was experiencing tremendous economic pressure. Part of this pressure was on their export market as a result of them having a very highly valued yen relative to some of the other global currencies, in particular the US dollar. So in order to compete in the US consumer electronics market, they had to price their products competitively, which meant pushing their manufacturing costs as low as they could be. That's the reason we see capacitors used in this receiver that are below the specifications laid out in the parts list in the service manual. It's because they were pinching every single penny so that they could remain competitive in this highly competitive export market. In fact, the parent company of Panasonic, Matsushita, had been subject to a number of anti-dumping lawsuits in the 70s that were a result of Matsushita pricing their televisions in the U.S. export market incredibly low in presumably an effort to sideswipe companies like Emerson that were still manufacturing their equipment in the United States. But all in all, would I buy one of these? Well, they can be found on eBay or Craigslist, and they run anywhere from, say, $50 a piece to maybe on the high end, $200. Are they worth it? Well, beauty's in the eye of the beholder. If you like it, it's worth it. If you don't, it's not. And is it worth it if you're trying to sell one? Well, it's only worth what someone is willing to pay. So I hope you've enjoyed this and maybe found it entertaining and maybe learned something. Thanks for watching. Have a great day.